Finding number is B240230. So I'll represent my group for doing the presentation about the algorithmic trade-off. So it's navigating the time-space continuum in the system architecture. So in system design, choosing a choosing an algorithm requires a balancing execution velocity with memory resources. So now we move on for slide 2. Okay, as you can see, this is a zero-sum paradigm using the balance scale model. In algorithm analysis, time and memory exist in a fundamental conflict. Decreasing execution time almost universally require an inverse increase in memory consumption. So this slide outlines 3 key pillars. So first, the inherent trade-off between time and space. Second, how we constrain low-power IoT and embedded devices prioritize space efficiency, while real-time systems prioritize latency reduction. Third, the Big O framework mathematically bind execution speed to storage capacity as in input size. So this slide is talking about the pebble game, which is covered the theoretical framework. So demonstrate that dropping memory below a critical threshold, it will forces the mandatory recomputation of drop values, and it causing execution time to explode exponentially. Branching the program proven that problems like sorting, the product of time and space, mathematically bound by a lower limit like omega times n squared. So that's all for my part for the slide number 1 to number 4. I will hand over to the next team member to present. Thank you.
Hi, my name is Devanandan, IT, Bachelor of IT. So now I'm introducing the three factors or the factors of pre-compilations, the dynamic storage, active pre-calculation, and pre-program the value for into table, the prevent the PCU from the executable to triple the three trees. So the pre the pre structures there will be the organized the data structures up to the actually to the lookup. Third is the data handling where the trace the active PCO's power is decompressed to the physical disk storage. Next is physio physiographic benchmark. This is the example for the example. The take actually O and to time to repeat the sub problem introducing introduce the memory well the table memo is reduced the time and complete to the downline and or teach or cross and maintain ON to actually space. The prefactoring and the place the setting into the P3 the X table before the runtime down stage operation from the link down to the constant time whatever that comes with the particle adding the new records requirement every requirement over it the rebalance the complex the storage execution. So now is sorting diagrams. Sorting diagrams are two types. The one is counting sort, quick sort. The counting sort is actually a frequency engine to achieve the endline to n plus k, execute the speed or execute time. The speed is a priority to the base memory actually record log n and place. Uh, but the risky is the n2 is and time is pure. So, right.
My name is Cik Muhammad bin Hussein. My student ID is B24120024. And now my slide is vector 3 data handling coefficient and slide content uncompressed access maximum footprint required by physical storage, but includes 0 CPU decompression text enabling instantaneous access. Compression access computational text converts critical disk space but demands significant CPU overhead to run decompression algorithms during retrieval. Presentation script, slide 10, detail vector 3, data handling, uncompressed data text, take up maximum storage footprint but include 0 CPU, decompression text for instant access, compressed data, converts this space but in process a CPU, computational text during retrieval to decompress data packets. And slide 11, architecture database required. Slide content full scan 0 and time minimal space sequential iteration through all records. Indexed lookup 0 log n time 0 and space direct access via HMAC B3 index by passing required sequential scan. Presentation script. Slide 11 applies this concept to database require a full table scan require minimal space but scan sequentially in 0 and 10. Ruling hash map or B3 index test 0 and auxiliary space to bypass full scan and achieve 0 log and lookup. And slide 12, hardware bottleneck. Wounded RAM slow, CPU demand aggressive pre-computation, memorization, and heavy B3 indexing. Low RAM fast CPU demands in place algorithm, quick short, compressed data routing, and real-time calculation IoT embedded. Diminishing return memory allocation ultimately drop as hardware costs future and at scale. And the empirical protocol. Number one, analysts identify primary system constraints. And number two, profile, isolate workloads, most expensive operations. Number three, evaluate forecast memory, footprint growth, and scaling behavior. And number four, measure delicate execution speed up empirically. Precision script set to map trade-offs to hardware environment system with abundant RAM but slow CPUs benefit from decomposition and indexing. Resource constrained system like IoT device need in place algorithm and real-time processing. Developer should follow our foster empirical protocol. Analyze constraint profile bottleneck, evaluate memory scalability, and measure speed up empirically. And our slide 13, conclusion the architect directive. Slide context, no universal standard, the perfectly optimized algorithm does not exist in a vacuum. Context is king, choose must be readily dictated by problem scale, hardware, ceilings, and operational goals. And strategy engineering system robustness require deliberate, measured, scalify across the time space continuum. Projection script to conclude on slide 13, the architect directive, there is no universally standard algorithm. Context is king, choose must be dictated by hardware constraints, and let's see goals. Strategy engineering requires measure scalable across the time space continuum. Thank you for your time, and our group are ready for any question.